Welcome to Unit 1.1, Video 1 in our AP video series. And our topic here is moles and molar mass. And so in this video, we are going to be answering the essential question, and you can put this in your notebook. What information does the periodic table provide about atoms? Now, in order to fully answer the essential question, I have some main ideas slash questions slash prompts that you need to be able to answer. And so we are going to answer those, and I have those color coded. And then from those ideas, in the summary of your notes, I want you in your own words to answer the essential question. So we're going to start off with this series of purple questions, and it says, what are the components or parts of the atom? So in an atom, we have three subatomic particles that we want to look at. And so we have the proton, we have the neutron, and we have an electron. I don't know if that showed up, an electron. All right, so there's our three subatomic particles. And then we can also see where their locations are, right? So we got our proton in the nucleus, our neutron in the nucleus, and then outside of the nucleus, we have electrons. So if we draw a simple sketch of what that would look like, we have in the nucleus, we have protons and neutrons. And then outside of the nucleus, we have these electron shells or energy levels, if you will. And there we see we have electrons. All right. And I'm just going to draw three there for no particular reason, but just to show that there are electrons outside of the nucleus. So there we see the components of the atom and their location. Now we should be able to express the mass of each component in kilograms and atomic mass units. So I think I have this chart in grams. That's of not, it's not great importance. All we want to do is be able to compare the masses of proton, neutrons, and electrons to one another for this, to answer this question. So we want to express the mass. When you express those, you can express them using this chart. But things that I want you to also do while you're expressing those is understand there is a large difference in the mass of a proton and the mass of an electron. And there's a large difference between the mass of a neutron and the mass of an electron. But however, protons and neutrons have a very similar mass. So we can see that the proton, whoops, I used the wrong tool there. The proton has a mass of 1.67 times 10 to the negative 24 grams, and that the mass of the neutron is 1.675 times 10 to the negative 24. So they're really pretty equal. However, the electron is 9.109 times 10 to the negative 28. And you may say, well, that doesn't seem like it's that big of a difference. Well, it is. So if we took the mass of an electron and put that into the mass of a proton, it would go into it 1,836.64 times. That means we would need over 1,800 electrons to equal the mass of one proton. So it is significantly less heavy, or it has a significant less mass. All right, so its mass is much, much less. And for that reason, the mass of the electron is not considered in determining the mass of an atom. We really only use protons and neutrons to determine the mass of an atom. Now, the mass of the atom can be expressed in grams, but it can also be expressed in atomic mass units, AMU. And you will also see people abbreviate AMU as just U. So we see that the proton has roughly 1 atomic mass unit, and the neutron is roughly 1 atomic mass unit. So close to 1 that we're going to say that each of those is 1 atomic mass unit. And so we can also see that the electron is significantly smaller. So again, this is why the electron is not used to determine the mass, because its contribution is very, very little. Okay, so let's see if we answered the question. What are the components or parts of the atom? We said those are the proton, neutron, electron. We were able to express the masses of the proton and neutron in grams and atomic mass units, and also the mass of the electron. We notice that the mass of the electron is significantly less than the mass of a proton, and significantly less than the mass of a neutron, and therefore the electron is not used to determine the mass of an atom. So let's move on. We're going to hold on to all those points of those purple questions, and we're going to move to the green questions. And so make sure you have all those, the question written under the question/main ideas in your notes, and then you're answering that over to the side. And then what information does the periodic table provide? So we have a periodic table here, and this is from ptable.com. And on the periodic table, you're going to notice a number in the top corner, and this number is the atomic number. And the atomic number represents the number of protons. It is only the number of protons. So make sure you know that atomic number is the number of protons, and an atom is identified by its atomic number or the number of protons. So lithium is the only type of atom that has exactly 3 protons. Lithium will never have 2 protons. Lithium will never have 4 protons. Lithium is defined by having 3 protons, or an atomic number of 3. So lithium also on our periodic table has a symbol, and that symbol is capital L, lowercase I. When you symbolize an atom, it must appear as it does on the periodic table. For instance, capital L, capital I would be incorrect as a symbol for lithium. It must be written as it appears on the periodic table. And then the last thing that we see is this number at the bottom, and this is the average atomic mass. And in reality, we can say that it is the relative mass. All right, that's a better definition. Now, these two terms are very, very close. So I said average atomic mass, relative mass, and I'll get into that in a little bit more and a little bit later on. So we can also see phosphorus. We have a symbol here of phosphorus. How many protons does phosphorus have? That's right, it has 15 protons. All right, what is the symbol for phosphorus? Capital P. And then what is its relative mass? Its relative mass is 30.974. All right, or you can say that it has an average atomic mass of 30.974 AMU. Okay, now there's another point that we can bring up, and this is not given to us by the periodic table exactly, but we can infer from the periodic table the number of electrons. So if we assume that all the atoms on the periodic table have a neutral charge, meaning they have no charge, then we know that the number of protons and the number of electrons must be equal. So we can see that a proton has a charge of 1+, an electron has a charge of 1 minus. So if we had the same number of protons and the same number of electrons, then the overall charge would be 0. For instance, if we know that we have a neutral charge atom of lithium, then we know lithium has 3 protons and 3 electrons. And we're not concerned with the number of neutrons right now. They don't have a charge. So the overall charge would be 0. All right, so our charge would be 0 because we have the same number of protons and electrons. The atomic number tells us the number of protons. Now, an atom can have a different number of electrons. Lithium can have a different number of electrons and still be lithium, but it cannot have a different number of protons and still be lithium. So this number in the periodic table represents only the atomic number, but because we know, if we know an atom is neutral charged, and we know that it has 3 protons, then it must also have 3 electrons. So you might be asking, well, how can we determine the number of neutrons? Well, let's make sure we finish answering our questions. So it says, what information does the periodic table provide? And we're supposed to draw an element as expressed on the periodic table and label the important information. So here we have one on the, just like we see on the periodic table, we labeled the atomic number, which tells us the number of protons, the symbol, and then we know this can be the average atomic mass, or a better term is the relative mass. All right, and then we also said that we can infer the number of electrons if we know that atom has a neutral charge. Okay, let's move on to the next question, and it's asked, what is an isotope? What information can be determined from an isotopic symbol? How do isotopes differ from one another? Draw a picture of isotopes to illustrate your response. And what does the periodic table provide about isotopes? All right, so what information does it provide about isotopes? So here we have isotopes, and I have this defined. And isotopes are atoms of the same element with different mass numbers due to a varying number of neutrons. So their mass number is different because they have a different number of neutrons. So we can see here that the mass number is equal to number of protons plus the number of neutrons. Remember, we said that the mass of an atom is based on what subatomic particles? That's right, the proton and the neutron. Why didn't we not include the electron? Yeah, again, you're correct. It's because the electron has such a small mass that we wouldn't even see it if we did add it to this equation, because it is so much smaller. So we say the mass number is the number of protons and neutrons. So in an isotopic symbol, and this is what this is here, it's an isotopic symbol. We have the symbol element. Now, how are you going to know what the symbol of an element is? Where can you get that information? You can get that from the periodic table. And how should you express that symbol? You should express it exactly as it appears on the periodic table. So it's very important. And so with your isotopic symbol, let's say that we did have lithium. We're going to put Li, and then we need to know the mass number. Well, I don't know the mass number from looking at the periodic table because all I know is the average atomic mass. I would have to know a specific isotope for lithium. Lithium may have an isotope of 7. And then so its mass number would be 7. And then it would have 3 protons. It has to be 3 because lithium does not have anything other than 3. So the question would be, well, how many neutrons does it have? Well, if the mass number is the number of protons and neutrons, and this is the number of protons, well, then 7 minus 3, that means this isotope of lithium has 3 protons and 4 neutrons. Now, if it was a neutral atom, how many electrons would it have? That's right, it would have 3 electrons. All right, so, and this is more inferred than we can't see it here. We just know since lithium doesn't have a charge, that it must have the same number of electrons. Now, how do we know what isotopes exist for various atoms? Well, we're going to get into that a little bit later on in mass spectroscopy. However, that information is going to be provided for you. So what does that look like? For instance, we know that carbon, there are 3 common isotopes of carbon. We have carbon, let me get the right pen, carbon 12, carbon 13, and carbon 14. What is the atomic number of carbon? So the atomic number of carbon. Where could I find that information? That's correct, the periodic table. So I go to carbon and I see in the top corner, top left corner, it says 6. That's my atomic number. So this is 6. That one is 6 because all of these are carbon, and carbon is defined by having an atomic number 6 or 6 protons. So if we were going to look at these 3 isotopes of carbon, what's the difference between them? Well, you might say, well, they have different mass numbers. But why do they have different mass numbers? Let's look at this. So carbon 12, as we would say, this could also be expressed this way, carbon 12. Carbon 12 has 6 protons, and 12 minus 6, 6 neutrons. Carbon 13 has 6 protons and 7 neutrons. Notice 6 plus 6 is 12. 6 plus 7 is 13. And then carbon 14 has 6 protons and 8 neutrons. So we see that each of these isotopes have a different mass number, but why do they have a different mass number? And the reason why they have a different mass number is because they each have a different number of neutrons. Their number of protons cannot differ, otherwise they would not be atoms of the same element. So in order to be atoms of the same element, they all have to be carbon, in order to be isotopes of one another, so they all have to have 6 protons. So this gets us to how we come up with the average atomic mass or the relative mass. And we're going to really differentiate between those two in this next set of in this next part of the lesson. So here we're going to take a look at this. So here's our isotopic data, and in order to come up with the average atomic mass, we take what is called an average, right? We take the average, but it is a weighted average. If we just took 12, 13, and 14, and we added those up and divided by 3, well, then the average atomic mass for carbon would be 13, when in fact, the average atomic mass of carbon is 12.011. So how are they getting that? Well, again, they're getting that through a weighted average. So what scientists do is take a sample of carbon and they run it through a mass spectrometer, and they can determine how much of each isotope exists, even what types of isotopes exist. So they did this and they got this data, and we see that for carbon 12, so what we're going to do is we're going to take the mass number and we're going to multiply that by the percent abundance divided by 100. And this is going to give us our mass in atomic mass units. All right, and we're going to do that for all 3. So we're going to take the mass number of carbon 12, which is 12. We're going to multiply that by 98.9 divided by 100. And we're going to get 11.868 AMU. Then we're going to do the same thing for 13. We're going to 1.1 divided by 100. And I encourage you to put this in your calculator. you're going to be doing calculations like this in another lesson for sure. But right now, I want you to understand the concept. And you're going to get 0.143. And then for carbon 14, it has a very small percentage. And you're going to get 1.4 times 10 to the negative 5. Now, what we do is we take all of those values that we get and we add them in order to obtain our average. And so when we add these three values, we get 12.011 AMU. Now, when we put a unit, atomic mass unit, with this value, that is called our average atomic mass. Now, you may notice on the periodic table, that value is the same. However, it doesn't have a unit. It's unitless. And so very technically, the value on the periodic table is the relative mass. Now we say, well, what does it mean to be a relative mass? Well, when you have a relative mass, you're relating the mass of one atom to the mass of another atom. That's why we call it the relative mass. They're related somehow, and they're related by mass. So how so? Well, for instance, carbon has about 12 times the mass of hydrogen. Nitrogen has about 14 times the mass of hydrogen. So the mass of carbon relative to the mass of hydrogen is about 12 times larger. So we can see that this tells us the relative mass, but we're not necessarily concerned about it saying atomic mass units. If I asked you what is the average atomic mass, then you would say that value using the expression atomic mass units. All right. And so I don't want to make that a big point, but I just want you to understand why we don't see the units on the periodic table. And this is going to come into play a little bit later on. So let's make sure that we answered our question. So what is an isotope? We said that an isotope are atoms of the same element with different mass numbers due to varying number of neutrons. And then we also want to know what information can be determined from the isotopic symbol. And so we see on the isotopic symbol, that's what these are. That's what these are right here. These are our isotopic symbols. And we see that we get the mass number and the atomic number. And what can we determine from the mass number and the atomic number? We can determine the number of protons and the number of neutrons. So from the isotopic symbol, you can determine the mass number and the atomic number. And from that data, you can get the number of neutrons. All right. And then this is just another way of expressing isotopes as well. Now, if we know they're all carbon, are we in the dark about how many protons they have? No, we simply go to our periodic table because we know our periodic table tells us the atomic number or the number of protons. So that is something that you can get there. Then the last thing I think it says, what does the periodic table provide? What information does the periodic table provide about isotopes? That's what I meant to say. It's not what it says. But what information does the periodic table provide about isotopes? It provides average atomic mass. And how do we get the average atomic mass? We get that by calculating the weighted average of the isotopes. And we can tell what the percent abundance of the isotopes are through given data. All right. And we'll say that for right now because we don't have a mass spectrometer. And most of that data is already out there for us to obtain. All right. And then lastly, it says differentiate between average atomic mass and relative mass. I kind of did that already. So remember, the average atomic mass is going to be using the unit atomic mass units. We're using the percent abundance to calculate that. And then the periodic table very technically uses relative mass, because it does not express the unit. So we can relate the mass of one atom to the mass of another atom with the relative mass. So what I want you to do now is in the summary part of your notes, I want you to answer the essential question. What information does the periodic table provide about atoms? We saw a lot of things. We saw the components of the atom. We were able to see different masses of those components. And then we know why electrons aren't used in that mass. And then we were able to draw an element as expressed on the periodic table, and we labeled the important information. So we labeled that we know we have it as the atomic number and the which is the number of protons. We can get the symbol from that. And then we also get the relative mass. And then we know about isotopes. And isotopes are very important to understand because we can't understand average atomic mass without discussing isotopes. So we can't understand relative mass without understanding isotopes. Now we know how those are calculated. And then, so I want you to put in your own words, using the ideas from our main ideas, questions/prompts in the summary, answer the essential question. Thank you for watching. Please like and subscribe.